So in this lesson, we're going to look at using what are called partial fractions to come up with sketches of rational functions. So this method will work provided we have a rational expression, a rational function, with a denominator with a higher degree than the numerator, and the denominator can be factored, which of course is going to reveal vertical asymptotes as well. Now keep in mind, we've looked at rational functions where the numerator is the higher degree, in which case I recommend using long division to break it up into a sum of functions, which usually reveals some strange end behavior asymptotes like oblique asymptotes or even a parabolic asymptote. We've also looked at when the numerator and denominator of the rational expression are both linear expressions. We looked at how to do that. We also divided in that case. So now we're finally on to the case where the denominator has the larger degree. So we're going to look at two examples, and let's get started. So in our first example, we have f of x is 3x plus 2 divided by x squared minus 4. So the first thing you do here is we're going to factor the denominator there. And it factors as a difference of squares to x minus 2, x plus 2. Which tells us right away that we have vertical asymptotes at x equals 2 and x equals negative 2. We could also start looking at intercepts. So if I set x equal to 0, I'm going to get a y-intercept. And in this case, that gives me 3 times 0 plus 2. Oops, got that written twice. Which gives us negative 1/2. Okay, so f of 0 is negative 1/2. And to find so that's the y-intercept. To find the x-intercept, of course, we set f of x equal to 0. Now, in order for a rational expression to be 0, the numerator must be 0. So we're just looking for when f of x is 0 happens when 0 equals 3x plus 2, or x is negative 2/3. And that gives us our intercepts here, 0, negative 1/2, and negative 2/3, and 0. So now that we've got the intercepts and the vertical asymptotes, the next thing we look at is end behavior. And remember, when we're looking at end behavior, that's also going to reveal more asymptotes that we might have, horizontal asymptotes or possibly oblique or slant asymptotes. Now in this case, we know the end behavior is 0. And the reason it's 0 is because the degree of the denominator is greater than the numerator. So when that happens, you always have 0. Now you could also sub large numbers in here to find that out as well. You could also divide everything by x squared. I'll do that. I'll show you that quickly. If you divide by x squared, you're going to get 3 over x plus 2 over x squared, all that divided by 1 minus 4 over x squared. And of course, when we do that, this approaches 0, this approaches 0, and this approaches 0 as x gets big. And so we have 0 over 1, which is 0. You can also just remember that if the degree of the denominator is greater than the degree of the numerator, then that's going to be your end behavior. It's going to approach 0 as x gets big because the x squared takes over. Now, we might want to know if we're going to sketch whether it's above or below, and I highly recommend you include that. Now, 0 is a nice number to work with because all we need to do is if it's above 0, if it's approaching from above 0, that means it's a positive number, and if it's approaching below 0, it's a negative number. So for positive infinity, we definitely will have a positive number here and have a positive number here as x gets big. So although this approaches 0, it will always be a positive number. So it's 0 plus a bit or 0 from above. And that's the notation we use for that. Now if x is negative, notice that the denominator will now be a giant negative number, like 3 times negative 2 trillion plus 2, definitely a negative number. And on the denominator, though, it's still going to be a positive number because when you square a negative, you get a positive number. So this one will actually be 0 from below. So there's a horizontal asymptote at y equals 0. I don't even need the above or the below to make that conclusion, but this will help me with my graph. And this will be true. This idea of a horizontal asymptote at y equals 0, that's going to be true for all the graphs we look at today. Why? Because one of the things we said was if you're going to use this method, it must be that the denominator has a higher degree than the numerator, in which case the end behavior is going to be it approaches 0. So the next thing we might do is we might actually try to come up with a sketch of what we have so far and see what we're missing. So we know the vertical asymptotes at x equals 2 and negative 2. We know the intercepts, and we know the horizontal asymptote. Okay, so there I've got my two asymptotes drawn and labeled, and I put the two intercepts in there as well. I'm not labeling them because they're kind of small and close together, and I don't want to crowd this too much. It's hard to draw a horizontal asymptote at y equals 0 and label it, so I haven't bothered with that because that's right on the x-axis. But my end behavior is 0 from below and 0 from above, so I can actually add that. I know that it's going to do the end of the graph is going to look something like this, right here, and I know over here it's going to look something like that it approaches those two. Now I may redraw those in a minute as I get the rest of the graph, but I do know that that's what that looks like. Now, how about the rest of the graph? I mean, you almost have enough here. You could start experimenting with some points, and you could pretty quickly figure out what most of this graph looks like if you examine what happens to the graph as it approaches the asymptote from each side. But I'm going to show you a method that'll give us the general shape, and that method is called partial fractions. Okay, and the idea here is that we're going to take our rational expression, we're going to break it up into a sum of functions, just like we've been doing with a lot of the other ones. So what I've done here is I've said there's some a value and some b value, so that when you split the denominator up, if you added these up, they would actually simplify to 3x plus 2. So presumably I could take two fractions, one with a denominator of x minus 2 and one with a denominator of x plus 2, add them together and come up with our rational function that we're working with. So what I'm going to do with this equation is I'm going to multiply both sides of the equation by x minus 2 times x plus 2. So that the x minus 2, x plus 2 on the left side of the equation is gone. The x minus 2 is gone here, but I'm still left with an x plus 2. And the x plus 2 is gone, but I'm left with an x minus 2. So now I've got this equation that should be true for all x. And the little trick I'm going to do right now is I'm going to take this equation and I'm going to start by subbing in x equals 2. When I do that, I'm going to get 3 times 2 plus 2 equals a times 2 plus 2 and plus b times 2 minus 2. So notice what happens here is the b is gone, and I get an equation just in terms of a. 6 plus 2 is 8, so I get 8 equals 4a, a is equal to 2. So it's kind of a strange little trick that you've probably never seen before, this idea that I have an equation here that's true for every x, so I can pick whatever x I want, and I can solve for it. And I chose x equals 2 because I knew that would eliminate the b. If I didn't choose x equals 2 and I chose some other number, say 3, then I would have had an equation in terms of both a and b, which I can't solve. Now you can probably think about what to do next. To solve for b, we can sub in x equals negative 2, and let's do that next. So I get 3 times negative 2 plus 2 equals, now the a is going to be gone, and instead I'm going to have b times negative 4. So plus equals b times negative 4. Or negative 4 equals negative 4b, and b must be 1. So I've chosen these values of x conveniently that allow me to solve for a and b. Had I chosen a value of x like say 3 and 5, for example, I would have had two equations, two unknowns with a and b. So I could still have solved, but it just would have been a lot more time consuming. So what I basically done is I found a and b here. And so now what I can say is that 3x plus 2 divided by x plus 2, x minus 2 is the same as 2 over x minus 2 plus 1 over x plus 2. And what I've done is I've actually taken our function, which I believe we called f of x, and I've rewritten it as a sum of functions. So it's really the same as the graph of 2 over x minus 2 plus 1 over x plus 2.
Now you might be asking why we've done this. Well, we're just
breaking up f of x into two functions whose graphs we know what they look like. One of them is 2 over x minus 2. That, of course, has a vertical asymptote at x equals 2. Okay, and it's like 1 over x. It's very similar to that. So it just looks something like this right here. And we also know what 1 over x plus 2 looks like. 1 over x plus 2 has a vertical asymptote at x equals negative 2. And basically the exact same shape. So it's going to look like this right here. And our resulting graph, f of x, is what we get when we add those two together. So again, back to this idea of adding two functions together to create a new graph. This plus this, or the blue curve plus the green curve. Now think about adding the green to the blue. The green and the blue does extend here, by the way. So adding the green to the blue. So to add those together, the green and the blue are both very small here. So I get this right here. And it just ends up looking like that, this part of the graph. It's the same as the green part, really. Okay, this is in black, our final graph. Skipping over this asymptote, you're adding some big green values to some small blue. So the graph does this, kind of follows the green, but a little bit below. The green starts to become small, but the blue becomes big, and so the graph does that. It's almost like you're connecting them together. In fact, I've shown you an example like this yesterday as well. And then over here, just follows the blue curve, like that. The green curve does keep going, but it becomes very, very small over here. So blue is very small here, so the black is basically the green, and here the black is just the blue because the green is small, and then you almost connect this green and blue. And so those black curves, and I know that they're not easy to see there, it's kind of a mess, but that's what our final shape of our graph looks like. So that's actually pretty helpful because that does give us our overall shape when we add these two together. So if I go back up to our sketch, we're going to do just that right now. And I'll do the best I can to draw it here. So I already, sure enough, we got the end behavior that we want. We get this right here. Okay, and then this part right here. Not like that. Let me try that again. A little bit more like this right here. Okay, and then the graph does something like this right here. Tried to get through both of those intercepts, might have missed one. Like that. Now, one thing I will point out, so there's our graph. Let's just take a quick look at it in Desmos. Okay, and there you can see it in Desmos. Now we got I've added the intercepts, okay, and we get the shape, exactly what we expected to see. Now, notice that something interesting does happen here, that this starts as a smiley face or half a smiley face. That's called concave up. And then somewhere in here, it changes from concave up to concave down, or half a frowny face. And I mean, it has to approach the asymptote like that. So when it approaches this asymptote, it's got to curve that way. But to approach this asymptote, it has to change its curvature so that it can continue to approach the asymptote without hitting it. Now, it sure looks like in this graph that happens right at 0 and negative 0.5. And it's fine to draw it that way. You don't need to worry about getting that point where that concavity changes. You don't need to have that in the exact correct spot for now. You need some calculus to kind of understand that kind of stuff. So we're just having the general shape, the asymptotes, the correct end behavior. Okay, we'll try one more example too. Okay, so we have another similar example. Notice again, we have a rational expression and the denominator is a greater degree than the numerator. And in this case, the denominator is already factored. So this again lends itself to partial fractions as a way of breaking down this rational expression. Okay, first though, let's start with easy stuff. Definitely there's going to be vertical asymptotes at x equals 7 and x equals -1. There are no x-intercepts, okay? G of x can never be 0 because in order for a rational expression to be 0, the numerator must be 0 and the numerator is 1. If you do plug in x equals 0 though, you will get -1/7 as for a y-intercept. So we do have a y-intercept. Okay, let's look at limits again, and similar to the other example, we are going to have n behavior that approaches 0 because the denominator is a greater degree than the numerator. Or if you wanted to, you could divide everything by, in this case, remember the denominator, although it's factored, it's of degree 2. It has an x squared in it when it's simplified. This tells us again that there's a horizontal asymptote at y equals 0. Now, it's helpful sometimes to know whether it's going to approach 0 from above or from below. So let's look at this first. Okay, so think of a really large number, positive number. You've got a positive numerator. As x gets really, really big, there's no doubt that x minus 7 and x plus 1 are positive. And so this is going to approach 0 from above because it's always a positive number divided by a positive number. Now, when x approaches negative infinity, big negative numbers, the numerator is still positive because it's 1. But you'd have a big number subtract 7, a big negative subtract 7, like -10 million, and -10 million plus 1. These are both going to be negative values. And when you multiply a negative by a negative, you get a positive. So this is going to be 0 from above. And we can start now by looking at all that information and sketching it, what we have so far. Let's do that next. We'll start with our vertical asymptotes. So there's our vertical asymptotes at x equals 7 and x equals -1. We could add our y-intercept as well, which we said would be at -1/7. So it's very, very close to the origin on this picture. So somewhere in there is fine. We could label it, but I find on this tablet, I'm just going to leave it alone or it just gets a little messy. So we also know the n behavior. We know it approaches 0 from above. So we can actually say that it's going to do something like this. Let me try that again. Something like this at the end. And same with over here. Interesting enough, we know that it doesn't cross the x-axis because it doesn't have any x-intercepts, and it's got to approach this asymptote and blow up to infinity as it hits that asymptote. So I can actually reason pretty easily that it's got to do this right here. And I think you could probably argue that you could actually figure out the rest of the graph as well. You know that this is a point, and you know that it doesn't cross the x-axis. So there's really only one way you could draw a curve that incorporates both asymptotes and crosses this point and doesn't cross the x-axis. So you're probably going to find it as something like, if you just look at the arrow here, probably do something like this right here. But let's still look at the partial fractions anyways, and that'll confirm that. Okay, so here it is using partial fractions. So I've defined these values a and b, okay, and I know that there'll be some a and b that when I add these together, I get a 1 with a common denominator of x minus 7, x plus 1. Multiply both sides of the equation by x minus 7 times x plus 1, and you get 1 equals a times x plus 1 plus b times x minus 7. You can also look at it this way. If you were to find a common denominator here, you'd multiply b by x minus 7 and a by x plus 1. And then you have 1 over x minus 7, x plus 1 equals a over x minus 7 plus b all over x plus 1. So then the numerators have to be equal. It's just another way of thinking about it. I'm not sure if that made sense or not. It doesn't probably really matter. Okay, so I got this equation I want to solve. It's true for all x. So it must be true for x equals 7. So x equals 7. And I will get that 1 equals 8a. And then I get plus 0b. So a must be 1/8. If I sub in x equals -1, then I can solve for b. I get 1 equals 0a plus b, in this case, times -8, so that b is actually equal to -1/8. Now, let's just take a look at what that looks like. So that means that our equation in this case, I believe I called it g of x can be written as 1/8 over x minus 7 subtract 1/8 over x plus 1. Now, we never need a fraction in a fraction. So the 1/8 just simply looks like this. G of x equals 1 over 8 times x minus 7. Subtract 1 over 8 times x plus 1. And there it is as a sum of functions. And we know what both of these functions look like, and that will provide us with the overall shape in the end. So let's just look at that next. Okay, so I've got both asymptotes drawn in, one at 7 and one at -1. Let's start with this equation right here. 1 over 8 times x minus 7. So that's a lot like the equation 1 over x, except it's been shifted to the right by 7. And then there's that horizontal compression of 8 or the vertical stretch of 1/8. That doesn't really change the shape of the graph too much. So it ends up looking like this right here. And this right here. Okay, the next one, we'll add that to our graph and I'll pick a different color. I'm going to do it in green. So it looks a lot, not like 1 over x, but you're actually adding, since you're subtracting, you're adding the negative. So it's a lot like -1 over x. It's been reflected and shifted to the left. So instead of being here and here, it's actually in the other two areas here. So part of it is right here. And the other part of it is down here. And of course it keeps going. Now we need to imagine what adding these two together does. So I'll do that in black. Okay, so I've got the green graph plus a little bit of red graph. So this is going to give me the black graph somewhere in the middle of those. I actually don't technically know whether it's below or above the x-axis, but the green takes off and so the black graph follows that. And so you get something like that. It's messy, but there it is. On the other side of the asymptote, we got big green negative and some red negative. So we're definitely in the negative. Goes up like this. Okay, then it starts to slow down, but eventually the red graph takes over and it follows the red graph like that. Then over here, we've got a little bit of green, but red is big, so we add those together and we're just underneath the red. We don't know for sure if we're above or below the x-axis. And there is the black curve, and that's our final graph. Well, it's going to be the shape of our final graph. Now, I said that when we add these two together, the red and the green, we technically don't know whether it's above or below the x-axis. Same with here. We technically don't know whether it's above or below the x-axis. It depends what's bigger, this negative number or that positive number. This negative number or that positive number. It depends what's bigger. But we know the end behavior of our function, and we know it approaches 0 from above. So we know that it is, in fact, above the x-axis. We also know it doesn't have any x-intercepts, so it doesn't cross the x-axis. That's not always going to be the case. There's examples like this where the graph does cross the x-axis. And you'll actually work on one of those in homework. All right, so I'm ready to go back to my nice graph and fill it in. Let's do that next. Okay, so let's go back here. Okay, and now we can fill the rest of this in. And like I said, there's no real surprise by this, okay? We already figured that, I mean, that's already in the right spot, okay, that we got in the picture down below, and it's just a matter of filling this in right here. Do it the best I can, try to draw that smoothly. Very hard on my tablet to draw smoothly, but that's it. Let me try that again if you can do better than that. Try this. Something like that right there, which really is the only possibility. We know it doesn't touch this, doesn't touch the x-axis there, by the way. We know it doesn't touch that x-axis because it doesn't have the x-intercepts. Now there's a turning point here. In here somewhere is a turning point. Now, you might guess that it's halfway between 7 and -1, and you might be right, but be careful, because rational functions don't have symmetry necessarily the same way like a quadratic would or something like that. Don't worry about where the turning point is. If you really want to know where that turning point is, then please take calculus with me next semester, because once you have a little bit of calculus skills, it will be very easy to figure out where that point is. But for now, we're not going to worry about that. Okay, that's the last example for this lesson. Thank you.